taking a journey way beyond what the human eye can actually see. We're diving headfirst into the microscopic world of nanomaterials. If you've ever wondered how the materials of tomorrow are being engineered to be lighter, stronger, and honestly just fundamentally better, well, you're absolutely in the right place. We're going to break down exactly how completely ordinary matter gets transformed into something truly extraordinary.
It's a space where tiny size creates a massive impact. We spend so much of our time thinking about large-scale engineering, right? Giant skyscrapers, massive rockets, sprawling bridges, all the big stuff. But the truth is, the most revolutionary engineering of our time is happening at a scale so incredibly small, it's completely invisible to us. We're taking the micro scale and using it to produce these massive real-world consequences that are completely reshaping industries across the globe.
Okay, let's dive into this transformation. Think about starting with a completely ordinary, high-purity rock, just something you might find out in nature. But then, through some really intense engineering, that raw material is fundamentally transformed. It gets shattered and evolved into these brilliant, high-performance particles. We aren't just breaking things down here. We're actually unlocking a completely new state of matter. To really grasp this whole concept, we gotta define what we actually mean by the nanoscale. To put it into perspective, a single nanometer is roughly 100,000 times smaller than the width of a human hair. Crazy, right? And when we shrink a material down to this level, we aren't just making a tiny version of the same thing. Actually, the very rules of physics start to shift. At the nanoscale, matter just behaves differently. This new size unlocks entirely new properties and new opportunities. It's not just miniaturization, it's basically giving materials superpowers that they simply don't have at a larger normal scale.
And this brings us to what we call the nano advantage, which is really the core logic behind why smaller actually means better. First up, smaller size. That equals way more surface area, which creates far more possibilities for chemical reactions. Second, enhanced properties. We're talking about materials that perform smarter, hold up stronger, and weigh significantly less. And third, limitless potential. We're literally solving today's absolute toughest engineering challenges so we can build tomorrow's future. So all of that sounds fantastic in theory, right? But it definitely begs a really direct, practical question. How do we actually engineer matter at the nanoscale? I mean, how do we take that ordinary rock we talked about earlier and train it, refine it, and modify it until it becomes a high-performance nanomaterial? Well, as you might guess, it takes a very rigorous, highly controlled process.
And this brilliantly illustrates the process. Think of it like a 6-step training montage for materials, the transformation journey. We start out with step 1, which is selecting high-purity raw materials. Step 2 prepares them through cleaning and mixing. Then step 3 is where the real magic starts, size reduction, right down to the nano level. That's immediately followed by step 4, surface engineering. Step 5 acts as our crucial checkpoint, where we characterize and analyze the results. And finally, step 6, the materials are application ready. It's just this beautifully structured pipeline, taking us straight from dirt to cutting-edge technology.
But I really want to zoom in on the absolute crux of this journey, which is steps 3 and 4. This is where the heavy lifting happens. During size reduction, we use advanced milling or synthesis to forcefully and, honestly, sometimes violently, reduce these particles down to the true nanoscale. But we definitely don't stop there. We have to transition from that violent reduction to some very delicate modification. In step 4, surface engineering, the surface of these incredibly tiny particles gets precisely modified. Why? Well, to enhance their stability, to make sure they're compatible with other elements, and to totally fine-tune their ultimate function. We're not just shrinking the material, we're custom tailoring its exact behavior. Now, what's really interesting about this slide is that you can't just engineer something totally invisible and, just hope for the best. You have to actually prove that it works. So in step 5, characterization, the newly formed nanostructure and all its unique properties are meticulously analyzed. We're looking for absolute precision here. It's an incredibly strict quality assurance phase, basically guaranteeing that the material behaves exactly as it was designed to before it's ever allowed to leave the lab.
When we put the beginning and the end side by side like this, the contrast is honestly staggering. We start over at step 1 with these humble raw materials that were just selected for their potential, and by the time we hit step 6, we've got precision-engineered nanomaterials designed for highly specific, high-performance applications. The ordinary has basically become extraordinary, all through the rigorous application of science.
But hey, let's transition away from the invisible science happening in a sterile lab and talk about the tangible reality that you experience every single day. Because at the end of the day, engineering is all about solving human problems. This isn't just cool theory. It's about where nano genuinely makes a difference in your world. These microscopic changes are about to directly impact the industries that shape our modern lives in a massive way. Just look at the sheer breadth of this impact. In energy, nanomaterials are the absolute key to better batteries and a truly sustainable future. In healthcare, they're unlocking targeted drug delivery, which means bringing therapies directly to the exact cells that need them. They're giving aerospace way lighter structures for higher flight efficiency, and they're giving our electronics the smaller footprints and faster speeds that we literally rely on every day. And for the environment, this technology is paving the way for cleaner air, pure water, and just a greener tomorrow all around. It literally touches everything.
So the crucial point is captured perfectly in this driving promise. We engineer materials at the nanoscale to unlock exceptional performance, drive innovation, and create a better world. It's an incredibly inspiring mandate, isn't it? It shows that by looking smaller than we ever have before, we are actually thinking bigger than we ever have before. Innovation at this scale isn't just a minor upgrade, it's a fundamental shift in what is physically possible.
As we wrap up this explainer today, I want to leave you with a thought. We've seen exactly how raw materials transform into these high-performance engines of change across healthcare, aerospace, and energy. The very rules of matter change at this scale. So what limitless potential will the nanoscale unlock for your tomorrow? Keep an eye on the invisible world, folks, because it is very busy building the future. Thanks so much for joining me, and keep feeding that curiosity.